Okay, good morning, everyone. My name is Thomas Brox, and I'm a professor for computer vision at the University of Freiburg in Germany. My group is focusing mainly on deep learning for video analysis and 3D vision, but we have also worked in a subgroup a little bit on biomedical imaging, so some of you might know UNet, for example. And I will also talk briefly about this today because it will also be the basis for what I then talk afterwards. So this lecture will be mainly about dense correspondence estimation with deep learning, and at the end I will also tell you a bit about cross dataset generalization, which is especially interesting in this context of correspondence estimation. So the lecture consists of 3 parts. The first part I will introduce encoder-decoder networks. So this is the basis for basically all dense prediction tasks that you have nowadays. So you can use it for segmentation, you can use it for optical flow, disparity estimation, you name it. Yeah, so everything that produces dense outputs in the end is actually based on such encoder-decoder networks. That's why I want to have a short tutorial. Some of you might know these parts already, but some of you don't. Then in part 2, I will focus on correspondence estimation with FlowNet. So this is a network that produces directly then a dense correspondence field. So this is something you can either use for optical flow estimations of motion in videos. You can use it for disparity estimation, so depth in stereo images. But you can also use it for image registration in medical imaging. I will focus here mainly on optical flow because that's where I was working on mostly, but you can transfer that to other applications. Yeah, and then in part 3, I will talk about cross dataset generalization. So that means you train on one dataset, and what you actually want is that your network works also on other datasets. And we'll look a little bit on when we can expect deep learning to do that job, and when we actually cannot expect it to do, and what you have to do to get a proper generalization to the data you're interested in. Yeah, so that will be the last part of this lecture. Okay, so let's get started with a typical image classification network. Probably most of you will know that. So you get some input image here, and the idea of deep learning is that you translate the feature specification into a learning procedure that produces a whole hierarchy of features, so that in the end you have kind of a classifier here that you also had in the past. Yeah, so also before there was deep learning, people typically for image classification used a classifier in the end, but just you had some predefined features that someone manually designed, and there were tons of papers that suggested different kinds of features that work better than the previous ones. Yeah, and by deep learning, this is replaced here by such a feature hierarchy, which is learned completely from image data. And the idea is that you have this ongoing abstraction in this hierarchy. So you have here the lowest abstraction layer where you're close to the raw data, and at the end you have the highest abstraction layer where you're close to the class label that you want to produce. Yeah, and you don't do that in a single step, this abstraction, but you do it step by step, and at the same time you can also reduce the resolution of the input data, so especially when you do image processing. You have here a very high resolution input, and you want to bring that down to very low resolution, namely a single class label per image. Yeah, so that's the strategy of deep learning as it came with classification. Now, often in image processing, in medical image processing, you're interested not only in a class label, so sometimes you are, if you just have to classify whether an image shows a certain disease or not, then the classification for the whole image is fine, but often you want to localize the origin of your output, so you want to actually have a pixel-accurate class labeling. Yeah, and this is called semantic segmentation, so for each pixel actually you want to have a class label. And you can do this, of course, with such a classification network by just looking at certain patches and then have a sliding window approach, and for each patch actually you run this classification network and you produce the corresponding class label. Yeah, and then you get a classification output for each pixel. Yeah, so this is something that has also been proposed already in 2012 from Schmidhuber's group, and it works. Yeah, so it's something that you can do. Do you still hear me? Yeah, good. But this patch-based analysis has some limitations. So the first one is that each decision that you do here, so for each patch you take a decision, each of these decisions is independent. Yeah? So you don't have connections between these decisions. Because you run an independent classification of this new patch and you don't consider what happened for the previous patch. The second problem is that this whole thing is rather slow because you have to run a full network for each of these patches, and since you have many patches, as many as you have pixels in the image, you have to run many networks at test time to actually produce the full semantic map. I must say this can be avoided if you use a clever implementation. Yeah? So if you do it naively, then it's very slow, but you can speed it up by reusing computations from the previous patches, and then actually this drawback goes away. The third drawback is that you have this patch size, so you have to define on how big is the patch that you're considering and which you're classifying. And this becomes an important parameter, and if you choose it wrong, then yeah, you get not the best result that you could get. And there's also a trade-off, yeah? So if you make the patches too small, then you lose context, so you don't capture all the information that you would need to classify the patch. And on the other hand, if you make it too big, then you lose the localization accuracy because the network might actually focus on features that are far away from your central pixels and yeah, then classify actually something else than what is localized at the center position, which you actually currently want to classify. Yeah, so there's always this trade-off, and you always have this tuning parameter that might not be optimal in the end. Yeah, so these are the limitations of these patch-based analysis. I want to mention that here because I still see very often that people use this patch-based analysis, although nowadays we actually have a better architecture to solve these tasks. So the question is, how do we get back the resolution? So what we lose with the classification network while doing all this downsampling in this feature hierarchy is we lose the localization accuracy. Yeah, in the end, we have here some representation of features for the whole image, and we put them into fully connected layers, but we don't know anymore where the information came from originally. Yeah? So which part of the image was actually the cat? You lost that information, and that you have to retrieve if you want to do segmentation. Yeah, so the question is, what can we do here to produce a high-resolution map again? And we can look a little bit into what people did in the past. So there have already been autoencoders for a long time. And what they do is they get an input here. They have kind of an analysis network, which is called encoder, to produce a feature representation, which is lower dimensional than the input. And then they use this feature representation to reproduce the input image, which becomes their output. So now they are increasing the feature functionality again, and they do that by a so-called decoder. Yeah, and so you have here some kind of a bottleneck where you have some abstraction in your feature representation, and you bring that from that, the decoder brings it up to the full resolution again. So here they often don't have resolution, they don't have images, but this is just a feature vector or data vector that you get in, and you produce another data vector, but you can also do that with convolutional autoencoders, and then you can also have here an image and here an image as well. Yeah, so we know already from these autoencoders that we can have such a concept where you can produce the full resolution at the output again. Yeah, so what we need is such a convolutional decoder here. Okay? Yeah, and this is actually quite simple. I will show you how. So this is an encoder. Yeah, so that's our classification network. And now you're actually just turning the whole architecture around. Yeah, so you have the abstract thing now as an input, and you have the high resolution image as an output. And then you can actually use the same architecture now with upsampling instead of downsampling as an image generation network. Yeah, so you can now do a synthesis of an image. Yeah, and this actually happened in 2014, where a couple of people came up with mainly the same idea. So this is one of the works from my group where we did some image generation with such a network. So we generated chair images from abstract inputs, so you could define what is the class label, what is the view from which you want to see the image, maybe also some additional parameters like the color of the chair and so on. And then you have here some fully connected layers that process this data. Then you have here some so-called up-convolutional layers that produce a high-resolution image in the end. Yeah, so here the image, and additionally we produce the segmentation mask. That's not necessary. You can also just use the image, but this is how the whole concept works. Yeah, so you, instead of these downsampling operations, these max pooling operations that you have in image classification, in this image generation, you have upsampling operations here. But actually, that's not a really big difference. Yeah, so the convolutions are still the same. I go a bit into more detail here. So how does such a up convolution look like? So it's basically just a convolution with a stride. Yeah, and you know that from classification there you also have convolution with a stride. It's just that when you do the downsampling, then the stride is in the other direction, so you have the stride here at the input and not at the output. And now for the up convolution. Okay.
Oh, you can do it works.
Ah, that works, so I can continue, okay. Yeah, so here for these up convolutions, you're placing the stride on this side. So that means you take here a feature vector from your lower resolution input, and then you have here the weights of your convolutional filter, and then you produce 4 outputs immediately, yeah, from a single output. This looks a little bit like magic, because from a single pixel you produce 4 pixels, but keep in mind that this is here a high-dimensional representation. Yeah, so this is just a visualize. Am I well? Okay, good. Yeah, so keep in mind that here you have a high-dimensional representation. Yeah, so it's, for example, 5 channels here per pixel, and these 5 channels actually can hold a lot of information that you can use to produce here a high-resolution patch, yeah, of 4 pixels. Yeah, so that's the whole idea of this up convolution, and everything else is the same. Yeah, so this is just a convolutional operation like in a usual convolutional network. That's why we also call it an up convolution. Some people call it deconvolution. I don't like that term so much, because a deconvolution is actually something else. That's the inverse of a convolution, and everyone who has worked with real deconvolutions knows that this is a complicated nonlinear operation, whereas this is actually very simple. Yeah, it's still a convolution. It's just that you replace the downsampling operator by an upsampling operator. Yeah, and basically as an intuition, you can see this as a learned upsampling operator, because you learn how to use these input features here to produce a high-resolution output. And this works very well. Yeah, at the same time, actually, there were these fully convolutional networks that also many of you will know already from Long and colleagues. And they actually use such a decoder as well for image segmentation. So they have here the classical encoder, so the classification network that produces a feature representation with a low resolution, but high dimensionality here. And then they have here, it's not really well shown here, but they have kind of a decoder here that turns that into a high resolution segmentation map again. Yeah, so that happened at the same time. And then there is UNet, which makes this a little bit more explicit. So there you have here this encoder. Yeah, so that's the classical classification network that does the analysis of the image. And you have here the decoder, which then produces, synthesizes the output segmentation from the representation that you have here. And in principle, this would already work, but what's quite useful is to add these skip connections here. They're not absolutely necessary, because in principle all the information could just flow through this bottleneck. Yeah, so you don't need to directly transfer information from here to there, but of course it's much more efficient. You need fewer neurons here in the bottleneck to get the same quality if you just copy the high resolution feature information from this level here directly here, and then it can be used at that point. Yeah, so basically before you downsample your information, you're actually just copying it to the corresponding level of the synthesis network. Yeah, so this is called skip connections. It's also very common. Okay, if we now compare this encoder-decoder approach with the patch-based analysis, then we see these advantages in contrast to the limitations that I've just stated earlier. Yeah, so first of all, this UNet is run once for the whole image. So that means you have a fast inference. Yeah, you don't need to run multiple networks for each patch, but you actually just feed this image once. You have a feed-forward processing, and then in the end you get your output. The second thing is that segmentation is done globally. So that means you have some implicit learned regularization here in the synthesis path. Yeah, so you don't need to have some extra regularization at the end because this is done here by the synthesis network. So it uses all the features that it gets, either the abstract ones from here or the copied ones from the input representation, and it learns on how to regularize that information to produce an output that looks like the ground truth. Yeah, so all this regularization is learned, and you don't need to run some CRF or so on top. I mean, some people still do that nowadays, but they also have a hard time to show that this really works better. Sometimes seemingly it does, but they have a hard time to show that. Because actually, in principle, it should not be necessary because all this regularization is part of these up convolutions here. Okay, and then you have this multi-scale analysis and synthesis. So that means you don't have any patch size parameter anymore. Yeah, so that's what I mentioned earlier. In this patch-based approach, you have to choose the patch size. And if you choose it too large, then you cannot localize accurately, then you get an over-smoothed result. And if you choose it too small, then you lose the context, the bigger context of the image. Whereas here, you can actually have a context that covers the whole image, but still you can localize accurately because you have all the resolution levels included here. Yeah, so you can produce super fine resolution details from the features here, and at the same time you can also go and have a full receptive field that covers the whole image and use that context information to produce the output. Yeah, so you have both. You don't have this trade-off anymore. And that's why these encoder-decoder networks are clearly preferable over patch-based approaches. Okay, now I show you a few results of where this UNet was used. So you can use it for binary segmentation. For example, here's an example from electron microscopy. So these are all data from ISPI challenges. Yeah, so it's this one. You can use it for light microscopy, cell tracking. That's something like this here. You have, yeah, here this histopathological data from another challenge. So you see, this is very different kind of data. And the principle of learning is beneficial here because actually you just train the network with this new data and then you can solve these tasks. So you don't have to design any new features. Yeah, so there's another example here where you get this segmentation. Yeah, so that would be very hard to manually design features for all these tasks. Yeah, so with learning, this is very straightforward. You only need the corresponding data. And we will get back to that. That this is, of course, an issue that you need the data. Here's another example from Freiburg. So we also help the medical people in our own place. So this is data from the kidney, and there's some segmentation of glomeruli. And you see that they're actually hard to spot. Yeah, so this part here looks very much like all this. So again, if you want to do some manual feature design, that's super hard to do. And you see that UNet actually produces very clear score maps for these parts of the images where these glomeruli are present. Yeah. You can also use that for multi-class segmentation. Yeah, it's just a matter of what you put at the output. Yeah, so whether you have just 2 class labels at the output or you have multiple class labels per pixel, then you can also use it for brain segmentation. So these are data from the MR Brains challenge. Or you can use it to X-ray dental segmentation, although there it worked much better than all previous approaches, but it still doesn't work well. So I wouldn't trust this. I rather trust my dentist than these results here. I think I get many holes here if I use this approach. Yeah, there's also a way to use that for instance segmentation. So nowadays there are a bit more advanced methods for instance segmentation than this. So some methods use some detectors and then use them for instance segmentation. So it's more a two-step approach. You can also use UNet for a straightforward instance segmentation, but it's not perfect yet, I should say. But here you see an example. So you have here a couple of cells that are touching each other, and actually you want to separate them from each other. And you see that it works in most cases, but sometimes they also merge together again. So it's not perfect instance segmentation. So this is also an example from the ISB challenge, and here you see how the simple concept works. So basically what we did is that the segmentation mask that you get here, you just artificially introduce some background at the touching cells. Yeah, so if two cells are touching each other and are actually not separated by background, you just artificially put at least one pixel in between these cells, and then you give them a very high weight. Yeah, so you use a weighted loss that puts more weight on these separating pixels than to the other pixels, and that means these background borders between the cells are much more enforced than the labels of the surrounding pixels. And that pushes the result to separate the different cells from each other. But of course you can imagine that there is no guarantee that there is not a single pixel that is not correctly labeled as background, and then the two cells are bound to the same connected component and are labeled as one cell. Yeah, so it's not a perfect approach, but it's a very efficient and fast approach, because again you have to run a network only once and you get the segmentation of all the instances. Yeah, then you can also use it for detection. So this is detection of cell rosettes and the zebrafish primordium. So they're actually these kind of rosette parts. So these later become parts of the spine of the, or actually there is the spine here already of a fish, and that's where certain parts that stick out of the fish in the end are generated, and they should be detected so that you can analyze them automatically afterwards. And you see that you can also use such an encoder-decoder network to produce these detections. Yeah, so afterwards you can use some non-max suppression to get the localization of the points. What you don't get here in this stage here is the scale or a bounding box or so, but you could potentially also regress the bounding box from these positions. Yeah, you would just need to produce more outputs than just the segmentation mask or the detection mask. You could also have another channel with the scale or the bounding box coordinates, and then you could also do that. This is not the most commonly used approach for detection. So typically they are working based on RCNN, where you have some bounding box approach that first produces proposals and then classifies these proposals. But actually, if you see that this RCNN approach also converged more to such an approach, because now they first have a network that produces the proposals, which is working pretty similar to such an approach here, and then they do this classification. So I think in the end these approaches will anyway merge to a single concept. You can also extend this to volumetric data. So in biomedical imaging you often have volumetric data, not just plain images. Here you see an example for electron microscopy of the mouse cortex, and again you don't want to use a slice by slice approach, but actually you want to classify the whole volume or segment the whole volume in one piece. And for that you can just use a 3D UNet, which is a straightforward extension of the classical UNet. So you see again you have here this analysis structure and here the synthesis structure, and the whole thing is just now working with voxels instead of pixels. And you see you have here then this first operation that does some downsampling. You do, since often in volumetric imaging you have different resolutions and along the different axes. Yeah, so you have typically in XY direction you have a high resolution, and then in Z direction you have a lower resolution. You see that also here. So you have a voxel size of 6 nanometers in one direction and 30 nanometers in the Z direction. And that's why you only downsample at the beginning the XY directions and not the Z directions. That's here, and then this goes down until you basically reach the same voxel size in all dimensions. And then you use here a 3D convolution and also a 3D pooling operation, and the same here for the upsampling part. Okay, so it's really the same principle as with the 2D UNet. Okay, then you can use that for semi-automated or automated segmentation. So typically it's pretty hard to manually annotate volumetric data. So if one of you have already tried to do that, then you know from what I'm talking of, because it's hard to visualize these things, and you have to see actually the 3D volume. It's not easy to visualize, and then you have to mark the things in 3D. So one way to make this easier is to use the 3D UNet and only label some slices in different directions, and then use the UNet actually to produce the full volumetric segmentation from that. So that's what we call semi-automated segmentation. So that's shown here. You have here the raw image, and then some slices. I'm not sure if you can see that well here. Some slices have been segmented manually. So this is basically a 2D segmentation that you have to do manually. And then from these sparse slices, you can produce the full volumetric segmentation with the UNet, because it just produces these other slices. And you can then label many of these images of in this fashion. And then you can also use the UNet in a fully automated fashion, where you just get the raw image and you directly produce the dense segmentation on a certain type of data set which you have annotated before. Okay, and that would also be end of part 1, and I think it's a good time to give you some time to ask some questions about these encoder-decoder networks before we go on with the correspondence estimation. Yes, there's a question.
So if you up-convolve, you said it's really like a normal convolution where you go from... the question is actually, can you also up-convolve? You have less channels than the patch you want to have eventually?
Okay, let me go back to the corresponding slide. I think you're referring to that.
Yeah, so in this
figure,
example,
right?
you go from 5 to 4, let's say, in a way. So that works.
So you mean if we just had 3 here and 4
Yes.
here? Yeah, it would also work. Of course, the information that is necessary to produce the output information should be somewhere present in the input. If it's not there, then you can only hallucinate things. Actually, that's what a network can also do quite well, hallucinate things, but then you're bound to your training data, and you're starting to maybe overfit to your training data. But also keep in mind, so it's not actually just these 5 values here that you consider, but you usually also have a local filter here. So also the neighboring voxels play a role in this upsampling operator. So this is a bit simplified here. So typically you have here a whole filter mask. And then you actually have more data. Yep. I'm not sure who was first.
Thank you for that introduction. I was wondering, we were using the 3D UNet for really large data sets, up to 1 terabyte. And you said the advantage would be that with the 2D UNet, you do not need to bother about patch size and regularization later on. But for the 3D UNet, we do have kind of to work on patches, because otherwise we cannot fit all the data into the VRAM. Would we need regularization later on then, or is it kind of implicitly also regularization over the patches?
Yeah, so of course you're fully right. So you have some technical limitations because you don't get the whole 3D volume and this whole 3D UNet into your memory of the GPU especially, because it's limited. Then you also have to use some tiling approach. That's still a bit different from a raw patch-based approach, because the patch-based approach always just produces one pixel. And if you do the tiling, you at least produce a certain window, and you have already some context there. Now it depends very much on the data that you have, of whether the necessary context to solve the task is already in the receptive field that you can afford to put into your memory. If this is the case, then you don't need some regularization in the end. If this is not the case, then it might be useful. I think some regularization is definitely going on, because at the direct neighbors of your output will always have this regularization, because you don't produce a single pixel, but you're producing maybe a 64 cube output at once. Yeah, and the regularization is already going on there. It's more the difficulty of the context in the input, that you have to capture that one. And if you have a huge image and the context of the whole image is necessary, well, then you have a problem, but you have that problem anyway. So I've seen a poster yesterday where they just use some more efficient representation in between, so that you can compute the different stages sequentially and then save some memory with that. So there are some other tricks on how you get around this memory bottleneck.
Okay, thank you very much.
And you were first, I think.
So I was wondering, how do you handle the pixels close to the boundary? So those are the pixels most difficult to segment actually in the network.
So you mean the boundary conditions, so how we handle those. So in the UNet, we actually use some mirroring in the original paper. Others are just use zero padding, so they just fill with zeros. I think both are valid approaches, although in some applications I wouldn't do the mirroring, because that actually hallucinates extra data that is not there. With the zero padding, the network actually sees that there is no data. So if the zero, it actually doesn't mean anything important in the raw data, then it can actually pick that up and learn that this is basically the boundary and learn what to do there. So that's why the zero padding is actually not such a bad idea in general.
Also, for the last slide, you showed some semi-automatic results, right?
Mm-hmm.
Is there any ways, like when you pick how to annotate those, and so that you get the automatic result better?
Well, you have to know much about the task if you want to save annotation effort, of course. So you need to have some representative slices that you annotate. If you just have a few neighboring slices, annotate them and nothing else of the volume, then probably you miss important information from the volume, and then this part is not learned. So it's typically better to have slices that are spread over the whole volume and also have multiple directions and not just a single one, than putting everything into one area of your volume. But apart from that, there is no general answer to that question. Of course, if you have empty areas in your volume, you wouldn't annotate anything there. Yes?
Yeah, I think you mentioned somewhere in your slides that it's hard to make CIF working as a post-processing step. So for segmentation, I'm wondering, can you elaborate it a bit to like which cases will it work and what cases it doesn't work?
I didn't hear the question well, because there was some extra
Like
noise.
the CIF, you mentioned CIF as a post-processing step for segmentation, and it's hard to make it working. So can you elaborate it a bit?
Yeah, so the point is that, let's go to so here in the synthesis part here, you have these learned upsampling operations, you have these convolutions here, so you actually can learn on how certain inputs produce an output that in the end looks like the ground truth. Yeah, so you're actually learning to produce a smooth output. If it's not smooth, then you get penalized for it via this supervision. Yeah, and that means you don't need to explicitly put a prior on smoothness to your output anymore, because it should already be smooth if your annotated data was smooth as well. That's what I mean. Yeah, so the regularizer is actually implicitly learned by the network. So that's the advantage of supervised learning. Of course, you don't have that in unsupervised learning, but that's a different story anyway. But in supervised learning, if your annotated data is smooth, then also your output should be smooth. If not, then it hasn't learned the task properly yet. Maybe one more question and then we go on.
Thank you for the nice lecture. I have a question. So typically training a unit, it takes quite some time. And can we still imagine to build some system for interactive generic segmentation based on unit? So on your last slide, you shown like, okay, I can just draw several slices, yes, and I can obtain the full segmentation, but I still imagine that it takes quite some time to train in this case, so it's probably not that interactive. Can we imagine to build an interactive system based on unit, like it's based on random forests, for example?
Mm-hmm. Well, the question was about interactive segmentation. So actually running the unit after it has been trained is very fast. So that would be interactive. Maybe not real time with 30 frames per second also, but still in an interactive mode. What takes long is the training, of course. So that's typical for deep learning. So you have this asymmetry between the training time, which takes long, and testing, which is very fast. And I don't know of any approaches that make this much faster. So training is slow in deep learning. Of course, what you can do is to have some pre-trained network that is already quite good and that you just want to adapt. And then this adaptation on only few samples, that might be relatively fast. So we actually did that. I will talk on the last slides of the lecture today about some things that we have done there. So that's much faster, but it's still not within a few seconds, but it still takes a few minutes to train and update the network. Okay, then maybe let's go on. So with part 2, and we will now talk about correspondence estimation with a network that is actually very similar to FlowNet from the architecture, but it's a very different task. So maybe first a few words about correspondence estimation. So what we want to do here is to produce a dense displacement field. Yeah, so for each pixel, you have a vector that says where this pixel is located in the second image. And this happens in optical flow estimation, that's motion. It happens in disparity estimation in stereo images. So from that you can reconstruct depth. So there you actually have a restriction because you only have to search along the epipolar line, so it's a 1D search problem. And you have it in image registration where you have, for example, 2 images and the patient moved and you want to compensate for the motion. Or you can even have 2 different modalities, so 2 different imaging modalities, and you try to put them together. That's a little bit more complicated then, but I think it could also be done with similar architectures. Today I will talk about FlowNet, so I will focus on optical flow estimation in the context of motion. We have also worked on disparity estimation. I won't show it here. We have not yet tested this on image registration, but I'm pretty sure that many of these concepts can be also used in image registration, and you're welcome to try that out. So this is the architecture of FlowNet, which estimates, again, in an end-to-end manner directly from 2 images that it receives as input. It produces the full dense optical flow field, in one go. And actually it's a unit architecture, as you can see, because you see there is this analysis path here that downsamples the information and produces more and more abstract features, and then you have here some bottleneck, and then you have this decoder part here, which synthesizes, in this case, the optical flow field and not the segmentation mask. So the principle is the same as what we have just seen in the first part. So the question was, when we started this, is can networks actually learn to find correspondences? Because the task is kind of different. In classification or semantic segmentation, you try to have some features, you search for these features, you try to find something that correlates, and then this is an evidence for a certain output class label. And we know that this can be learned, but for correspondence estimation, you actually have to compare parts of the input. Yeah, so there is one part of the input that matches a certain part of your input as well. Yeah, and now the network has to find these correlations in the input data. And it was not clear that this would work. Nowadays it's more clear. Actually, everything seems to work with deep learning in a way. That's not true, but many things work, and also this worked. Yeah. So, but I want to highlight here that this learning task is quite different from these recognition tasks that you're used to, maybe. And we'll get back to that later when we talk about cross dataset generalization, because actually this difference also helps us to generalize better on this task than in recognition tasks. Okay, so yeah, that was one problem. We didn't know whether this would work at all. The second problem is that you don't get training data so easily. I mean, it's anyway not easy to get training data in large amounts, but if you think of classification, there you get an image and you have to assign a class label. So that's actually a single click or so. For segmentation, it's a bit harder. So you have to draw some boundary outline and so on. It's already more effort, but it's also something that a human can do. For correspondence estimation, especially for dense correspondence estimation, that's actually impossible that you do that by manual labeling. Yeah, so no one wants to draw a corresponding for each pixel in the first frame where it would move in the second frame. And actually no one could do that really. Yeah, for some nice points you can do that, so there are some sparse correspondence fields that you could produce, but not a dense correspondence field. And correspondingly there's also very little data sets that were available. So there's this Middlebury data set for optical flow estimation where they put a lot of effort into getting ground truths for real images with some fluorescent markers and so on at high resolution images. They produced 8 frames with ground truths. This is definitely not enough to train a deep network of the size that I've just shown. There's the Kitty data set. It's in a driving scenario where they have a laser scanner on the roof of the car, and they know the motion of the car, and if they combine this depth estimate and the motion of the car, they can also produce the ground truth optical flow field. It's sparse data, but still relatively dense, so it would be good enough, but it's also just 200 frames that are that were annotated here. And then there are synthetic data sets, so basically open source movies that have been rendered by people, and one of them is the Sintel movie, which has been used for a data set, and there you get about 1,000 frames with ground truth. But even that, so this starts to be good enough for training a deep network, but there's a high chance of overfitting if you train on these amounts of data. So what we actually wanted to have is something around 10,000 images or more. The question, where do we get that from? So getting realistic data with ground truth is very hard in this context. So we just dropped the realism. Yeah, so we said, okay, realism is overrated. We want to estimate optical flow, and that need not be necessarily some real optical flow or some real moving objects. And we created this flying chairs data set where we just took some flicker image, transformed it a little bit, and then put some chair images and also transformed them a little bit, and then we got some optical flow fields. Yeah, and now we know the ground truth for the image pair. You see, it's not realistic at all, but it somehow looks like real images on first glance. And the surprising thing was that if you train a network on this kind of data, this generalizes to other images. Yeah, so you can now apply it to, for example, the Sintel data set, and you get a reasonable optical flow field, although you trained it just on this very artificial data. Yeah, so that's something, we'll come back to that in part 3 of this lecture. This is something that is special for these non-recognition tasks, yeah, like optical flow estimation. You won't get that so easily if you want to do semantic segmentation. So that, what I first showed was an architecture like UNet, where you have, where you just stack the 2 input images and you analyze them together. We also tested another architecture, which is a bit more engineered for the task of correspondence estimation. And in this network, we call it FlowNet C. C stands for correlation. There we have a Siamese network. So that means each image is first analyzed by some by some small network that produces some feature representation. And the same for the second image, and here you have weight sharing. So that's why it's a Siamese network. So the weights between the filters of this part here and this part are the same. So basically you learn to produce a feature representation which can later be used for matching. So that's what this part does. And then you have here an explicit correlation layer which produces a cost volume. So this is more like classical block matching approaches and so on, where you have some feature representation for the blocks, and then you run some correlation, and then you get a cost volume, and yeah, then you have to either you directly produce the displacement field from that, or you do something fancy on top of it. The fancy on top of it, what we do is we now have our encoder-decoder architecture, which analyzes this cost volume and produces the optical flow field. Yeah, so these are the two architectures that we used. This part is actually identical. Yeah, so the decoder is the same in both architectures. So we call this FlowNet S, and this one FlowNet C. So FlowNet S for simple and the C for correlation. Okay, and then you can see here in the video that it works in practice. So you see here frames per second, 10 frames per second. That was on a laptop. You can also get this to real-time performance on today's graphics hardware. Yeah, and you see it produces reasonable optical flow that is also general enough, although it has only been trained on this flying chairs data. So there's no chair in this image. Well, there is one, but someone is sitting on top of it, so that's not the main part of what the network has to do here. And you see all this motion here is estimated well. I didn't mention this color code here, so that's a typical color code that you use in optical flow estimation. So the color indicates the direction of the movement, and if it's white, it means there is no motion. If it's a more intense color, then there's a lot of motion. Yeah, so that's the visualization that you typically use in optical flow estimation, to both see the details of boundaries, for example, but to also see the direction of the movement, if it makes sense. You see the student had a lot of fun. You can also can go outdoors with this, yeah, since it runs on the laptop, and then you can get some data there. And also there you get some reasonable results. Although if you look carefully and you see already that it's kind of noisy, yeah? So in the background there's some flickering, there are some artifacts. So this was the first version of the FlowNet, which worked surprisingly well because we didn't expect it to work at all. But actually, from today's standards, it's not really good. Yeah, and especially this network was an underperformer on small motion. Yeah, so here's an example where there's actually very little motion. Whoop, yeah, there you see it. Yeah, so there's not much motion. The baby moves a little bit, and you see here in the FlowNet you have these noise artifacts here in the background. This is partially due to some compression artifacts. It's an example from some action recognition dataset which has very bad compression artifacts. But this is not the only reason, because you also see here a classical variational method for optical flow estimation. It produces much smoother results and also gets the motion of the kid much better than the FlowNet. Yeah, so in the small motion cases, the network was not really good and not competitive to variational methods. And you can make that even more explicit if you just put two identical images into the network. Then a variational method says, well, that's very nice. I start with a zero flow field, and wow, it perfectly matches, so I keep it there. So you get the perfect optical flow output. But the FlowNet actually produces some artifacts. So it hallucinates some motion that is actually not there. I mean, I overemphasized this. It's not that bad. I just magnified the flow vectors, but still, actually, you should get a zero flow field. It's trivial to produce that, but the network cannot do that. Okay, so there was some problem with small displacements, and there was generally a problem with accuracy, and that's why we created FlowNet 2, which has two major changes. So the first one is an architectural change. So we're stacking networks and use motion compensation. So that actually the first network is doing the same job as what we have just seen before. So it produces the first optical flow field. And then these other two networks are actually responsible on refining this initial flow field. Yeah, so they can specialize on the refinement task and don't need to do the thing from scratch. So that's why you take the flow here, apply it to the second image, so you warp it. So there's those people who worked on registration or optical flow estimation know that this image warping is just a motion compensation with the optical flow that you have computed so far. And then the new network gets also this warped image as input. Yeah, so it has already compensated the optical flow that has been computed so far, and then the next network here can focus on the remaining errors and can try to remove those. Yeah, and we tested different stacking hierarchies. Of course, you could also stack 4 or 5 networks. Of course, it also gets more and more expensive. Yeah, so you want to stop it at one point because the benefit that you get from stacking more networks on top of it at some point saturates. Yeah, so 2 is actually already giving you 80% of the benefit, and stacking a third one gives you then 95% of the benefit, and taking a fourth one wouldn't help you much anymore. What we also did is add some explicit small displacement network that was trained on just small displacement data, because we thought at that time that would be necessary, that you have 2 networks trained on large displacement and small displacements, and then you combine them here. Actually, now we know that this is not necessary. Yeah, so you don't need this small displacement network anymore. You just have to run a proper training schedule that involves both large and small displacements during training of this part here. And if you have that, then you don't need an explicit small displacement network. I will also get back to that in the third part of the lecture. Yeah, so that was the first change, that we stacked these networks and used motion compensation. And the second one is an improved data and training schedule. Yeah, so we optimized on the data, so starting from these flying chairs to using something more sophisticated, and also introduced some training schedules on data sets. And I will talk about this later in part 3. Here we'll show that this now improves results quite a lot. So this is especially on real data and on data with small displacements. You see here a few real images, and this is a state-of-the-art classical method, so it's not a network-based approach. And this was the old FlowNet, and you see it, especially here, it produces a lot of noise and actually it doesn't capture this moving person here. And this is now the result with the FlowNet 2, so this improved FlowNet, and it has very clean flow fields without that noise, very sharp boundaries, and so this is now really, it can reach state-of-the-art performance and is competitive to all the variational methods that are available. Here you also see a direct comparison in the video. So on the left, the old FlowNet S, and here the new FlowNet, and yeah, there you clearly see the difference between the two, so on how much the stacking and the improved training data helps. There's less noise, sharp boundaries, and it's overall a bit more reliable. And we also have multiple variants. Of course, in your network architecture, you have a couple of ways on how you can slim the network down. So you can have a very small network that runs at 140 frames per second, and you have this fancy network that has the largest size and runs at 8 frames per second, and you can choose what you need for your application, where it's more important to be fast or if it's more important to be accurate. Yeah, so, for example, here we still have a stacking of 3 networks, but we used slimmer architectures, so we had each layer has fewer channels. And then results are a bit worse, but it also runs 3 or 4 times faster. And this is actually, this is just without the stacking, and then you see you getting down to something like 140 frames per second, but you have a quality that is comparable to this first FlowNet. Here you can also see this accuracy runtime trade-off. So this axis here is the accuracy, so you want to go down to in this direction, and this is the runtime at a logarithmic scale, the runtime in milliseconds per frame. And you see here the Pareto front by FlowNet, Yeah, I mean, this is an old figure. Nowadays, there are more network-based approaches that are also somewhere in this area. But at that time, there was just our old FlowNet, and there were all these other approaches. And you see that they are orders of magnitude slower at the same accuracy. So these network-based approaches have a very good accuracy runtime trade-off. They're not necessarily better. You see that here the flow fields and FlowNet 2 reach the same accuracy. It's just that here you are 800 times faster. Here's a table of that is more current. So that's which shows that it really produces state-of-the-art optical flow estimation. So on this was this flow fields that I showed earlier. That's an older approach, but there's also here that's some classical variational approach which gives you 5.1 as an error, and the FlowNet 2 has 5.7. And there's another network that just appeared this year at CVPR, which has 5.0 and is state-of-the-art on Syntel. On Kitty, actually the FlowNet performs a bit better. So you see these network-based approaches are really on par in terms of accuracy, but they are much faster than these classical approaches. Here's some latest work that we did where we first improved a little bit on the FlowNet by using here some residual connections in this stacked network. Yeah, so you actually can copy the output of this network and just attach it here. So that's the idea of a residual network, and you can do the same here again. That helps a little bit. And the main thing what we tried here is whether you can also produce occlusion information. That's something that you often don't have in registration, but sometimes you might also have it, is that one object occludes the other due to the motion. Yeah, and of course in the occluded area you cannot compute the correspondences because you only see it in one image, the content, but in the other image it's not there anymore. Yeah, so you cannot compute a correspondence between the points. And it's therefore quite useful if you can detect these areas to, first of all, to make it explicit to the network that in this area it has to hallucinate the optical flow and cannot actually measure it. And second, it can be useful to know the occlusion areas for some tasks. Yeah, so for 3D reconstruction and so on, it can be often quite useful that you know that certain parts are occluded by others for depth layering and other parts. So that's why we have here a network that produces not only the optical flow but also the occlusion maps. So this is now a classification task whether a pixel is occluded or not. And you can just train it together with the flow network. We tried many more complicated things, for example, feeding back the occlusion to the optical flow estimation and so on, and it all didn't improve results, which told us that the FlowNet already did some occlusion estimation because it was so relevant for the task of optical flow estimation that it automatically learned it, even without having ground truth on occlusion maps. So that's quite interesting. So basically what this network does is just it makes the occlusions that have been estimated by the network anyway explicit to humans so that you can also use them at the output. And the same happens for motion boundaries. So we also produce motion boundaries here. And also those can be useful for some tasks. So if you want to have motion based segmentation or so, then you can use these motion boundaries for this purpose. Yeah, so that's what I mentioned, residual connections and occlusion and motion boundaries. And the nice thing is you get this extra output for free. So you don't need a bigger network or do anything fancy. You just produce these extra maps. Is there a question? No. Okay. Good. So here you see a result of that. So these are two images with quite a lot of occlusion because there's fast motion. And this is the ground truth occlusion map. So again, this is a synthetic example here where you know the correct occlusion from the rendering engine. And then this is the occlusion map that is estimated by FlowNet. Yeah, and it matches the important occlusions very well. Some details are missing, but that's quite common. And if you compare that to other occlusion estimation approaches, so here is the FlowNet one and here the others, then this is much more accurate than what you got before. So people wrote whole papers on just occlusion estimation. In the past, not so many as in segmentation, but there were a few papers, and you can actually, with a almost trivial approach, extension of FlowNet, you can actually clearly beat them. Yeah, so you see here, that's the F measure, and you're much better by just producing the occlusion outputs. So typically what is done in occlusion estimation, so the straightforward approach is that you compute optical flow in the forward and the backward direction, and then you're testing whether your forward vector plus the backward vector gets you to the original point, and if not, then you mark it as occlusion. And that's shown here in the first row. So if you use actually the same FlowNet and you just use these forward-backward constraints, then you see you're much worse than this. Yeah, so there's still a lot of extra things that are going on in the FlowNet to produce these occlusion maps. Okay, so the next question that we had was how reliable is the estimated optical flow? So so far we only produce a single flow field, but we actually noticed that in areas where it's hard to estimate optical flow, this optical flow was flickering. Yeah, so we actually saw that the network was not really sure on what to do in these areas. And we thought that this could actually be a way to produce some confidence measure, some uncertainty measure on how good is the flow. Is the network certain about the flow or is it not? That would be quite some important information. So in my group, also the car industry is interested in these results, and of course they want to know on how reliable the output is that we produce before they do something with the car. And what you can do is to apply some Bayesian deep learning. Yeah, so there are some works already since the 90s that turn networks into probabilistic approaches. Yeah, so typically a network is just a mapping approach. It has nothing probabilistic. It gets some input and it maps it to some output. But you can introduce some introduce random variables, so you can treat the weights of your network as a random variable, and then you can also apply priors to these random variables, and then you have a Bayesian approach. And there are a couple of approaches that have been used there: MCMC sampling, variational inference, probabilistic backprop, and so on. The problem of these approaches is typically that they are not efficient if you have many random variables. And in networks, you have millions of these weights. Yeah, so you don't want to apply sampling to all of these millions of weights. So that's why most of these approaches are intractable for large networks. So these things are sometimes tested on MNIST or so, but not on a FlowNet or UNet or something like that. One exception is this MC dropout approach by Gall and also Kendall and Gall, who used that also for semantic segmentation, and they had a strategy to make this efficient enough so that it runs on huge networks for segmentation, for example. And what we wanted to do is to test if this MC dropout approach is actually the approach that one should do, or if other alternatives actually work better. So maybe a short background. So you have learned about dropout already, I heard. So dropout is a typical regularizer that you use in deep networks, that you just remove a couple of neurons during training, and at test time you replace them by 0.5, or depending on the dropout rate that you had. Yeah, and it's used for regularization. And actually people showed that this dropout can also be regarded as kind of a sampling procedure in a Bayesian setting. Yeah, so basically your weights are sampled by dropping out the weights every second time or so. Yeah, you can regard this as a discrete random variable, which is 0 or 1 at one point. Yeah, and then you can use that for uncertainty estimation in this Bayesian setting. But there can be also other options, and I will show you a couple of them now. And we tested them all for the FlowNet approach. So the first one is to use ensembles. Yeah, so instead of a single network, you train multiple networks. Yeah, so you see that here. So typically you just train a single one which estimates the optical flow, and now you would just train multiple different networks that all estimate optical flow. And yeah, it's easy to randomize the training because anyway it's stochastic gradient descent. You can shuffle your data and you always get different networks if you run that multiple times. Yeah, so that's the randomization process that produces such an ensemble of networks. And then you can just run all these networks also at test time. So that means you get multiple outputs here, and then you can compute the mean and the variance from these outputs. And that would be your uncertainty estimate. So you can use the variance as an uncertainty estimate. If the variance is very small, that means the network always produces the same output, or all the networks produce the same output. So then the networks seem to be quite certain about this location in the image. Whereas if the variance is high, that means all the different networks produce different outputs, so there's uncertainty in this location. Yeah, so that's the idea. The downside of this is that you have to train and run M networks to get the mean and the variance estimate, and if you want the statistics to be reliable, then M should be large enough. Yeah, so this whole thing scales linearly with the number of networks, both at training and at test time. And that's of course not so nice. An alternative to that is to use predictive uncertainty. So it's a single network that directly produces the mean and a variance estimate. Of course, this is not a statistical measure of variance or a statistical measure of mean, but it's just the output of a network. But you can still try that. And what you need, of course, is a different loss function. Of course, you cannot just train for a single ground truth loss, but you actually have to use some log likelihood. So you want to maximize the log likelihood over your data set, and that way you also include the variance as a parameter. So you produce both parameters of your network, both the mean and the variance, whereas typical networks only produce this mean estimate. Yeah? So the advantage is you have a single network that you train, it predicts these parameters of your distribution. So here it's a Laplacian or a Gaussian, yeah, with these two parameters, but it could be any distribution which could also have more parameters. Yeah? We just kept it simple. And then you maximize the log likelihood of that distribution with regard to your weights. Oh, that's the second approach. And then you can also combine these two approaches. So you can use an ensemble of these predictive networks, and then you get a predictive ensemble. Yeah, so then you have the mean and variance estimate of each network in this ensemble, but then you also have the statistics across the ensemble. Yeah, and then by the law of total variance, you can also combine the variance estimate from the prediction and the variance estimate from the frequencist approach, so the ensemble itself, and you can combine it together to get a better estimate of the variance. Of course, the downside here is, again, you have to train and run M networks to get these statistics. And then we also invented a new approach which produces directly multiple hypotheses with one network. Yeah, so we have a flow net which not only produces a mean and a variance estimate, but actually has the chance to produce multiple hypotheses. So if the network is not sure about the optical flow at a point, then it can just produce these multiple hypotheses, and it's the loss is designed such that it's only penalized for the best performing one. Yeah, so that drives the network to produce diversity in the hypotheses. Yeah, and then in the end you have another network that combines all these estimates to a single mean and variance estimate. So the advantage here is that you use kind of an ensemble, so you produce multiple hypotheses, but you don't need to run an ensemble of networks because a single network is doing the job. So it's much faster, both during training and testing. So here's an overview of all these approaches. There are these empirical ensembles. Then you have the predictive distribution, a single network that produces both mean and variance. Then you have the predicted ensembles, which is an ensemble of these networks, and then you have this flownet H, which produces multiple hypotheses. And these ensembles, we also tried multiple ways to produce the ensemble. So one is MC dropout, that was the one that was used by Gall, but we also used other ways to produce ensembles, for example, bootstrap ensembles or snapshot ensembles. These are other efficient ways to produce ensembles. And then we tested them on the optical flow problem. And the way on how you can measure the performance of your uncertainty estimate is to produce a so-called sparsification plot. So the idea is that you remove those estimates that are most uncertain, those you remove first. And if your uncertainty estimate is good, then your accuracy should get better by removing these bad estimates. So if you really estimate the uncertainty well, then you should remove the bad estimates first. So that's why this should be a monotonically decreasing curve. And there is an oracle, so if you would do this selection based on the ground truth error, then you would get this curve here, the lower one. So that's the best you can get in this sparsification plot. And the real curve that is produced by your uncertainty estimate is this one. So that means if this curve here is close to that one, then you're doing a good job with your uncertainty estimates. And we also did that by now just looking at the area under the sparsification and use that as an error measure. So you can just plot this area under the curve, and then you can compare results there. Okay, and we did that for all these tested methods. And yeah, this looks a bit overwhelming, so I summarize this for you. So at the top here, so these are the worst performing approaches, are the ensembles. So the top one is the MC dropout. So actually the one that Gal suggested is actually was performing worse. So you have options to be better than that. At least for optical flow, we didn't try it for segmentation. And these are the other two ways of producing ensembles. So this was this first class of methods. Then here are the predictive ensembles. So they're the next best methods. And also interesting is that this red curve here, that's the one where you have actually a single network which produces the mean and the variance of the parameters of the distribution directly. And it's actually not doing much worse than the ensembles. So actually you can save the time to run a full ensemble on that. Only the bootstrap ensemble was a bit better. And then the last one is this FlowNet H, which produces these multiple hypotheses, and from the hypothesis derives the uncertainty estimate. And the green curve is actually a bootstrapped ensemble which is combined with the fusion network that we also have for the FlowNet, just to make sure that it's not just the fusion that leads to the improvement, but really both together. So you see, you can get quite some improvement over the MC dropout approach. Here you see some results on some real videos. So here, for example, you have something without any structure, so you actually cannot estimate optical flow, you can only hallucinate it, and also the uncertainty is high in this area. So here it's the same for so in the places where the ball is thrown, you hardly see it, so there the network is uncertain about the motion in this area. So it actually does a pretty good job in estimating those parts of the image where it's hard to estimate the optical flow. And on the right there was just some other methods for comparison, which mainly focuses on the boundaries of the object, which is also reasonable because at motion boundaries you're also uncertain, but this is not the only reason for uncertainties. So there are other areas that should be marked. Okay, so that would be the end of part 2, and again I would offer you to ask already some questions here.
So Thomas, I noticed your results like hit a limit where the EP is about 3, right? In one of your graph, you have when you compute the error, the average EP is about 3. Looks like you cannot go below that.
You mean here?
Like your FlowNet 2, for example, right? The performance, I think you have a plot where you benchmark a lot of approaches and then you compare the computational complexity versus the average EPE number.
Okay.
Right?
Yeah, let me go back to that slide maybe. Let's see if I find it. This one?
Yeah, anyway, so it doesn't matter, but my question is, this one, right? So my question is, what exactly defines the limit of your error? Like, what it will be absolutely lowest error you can achieve for any approach?
Well, I think there is no limit. This is synthetic data, so in principle there are no errors in the ground truth as such. So you could, in principle, reach 0 error. But this is probably hard to achieve because there might be not all the information available to guess that result. But I think there is no limit. So typically the limit that you can reach is the accuracy of the ground truth. So if your ground truth is actually has an error of, let's say, 2 or so, then you cannot reasonably get beyond 2. Yeah. But that's not the case here. It's so at least on the Syntel data, that's synthetic data, so the ground truth is perfectly correct. At least we assume so. There are some issues. I remember that Michael Black told me that there are some issues even in the synthetic movies that the rendering engines do some dirty tricks for the hair, for example, and so on. But typically, I think they removed all these critical cases where they couldn't rely on the ground truth for this Syntel benchmark. So there's still room for improvement here.
Hi.
Over there. There was a question. Over there.
Where?
Well, for the first version of FlowNet, you just introduced 2 architectures. One is FlowNet S, and the other is FlowNet C. But I'm wondering, how would you interpret why the FlowNet C can work better than FlowNet S? I mean, that one with 2 branches.
So how we integrate this?
I mean, how would you interpret why FlowNet C can work better than the FlowNet S?
Why FlowNet C was better, or?
Yeah, so FlowNet C, so I mean the one that with 2 branches first.
Well.
So you show 2 branches. One is just single channel, and the other one is first with several layers with 2 branches, and then. So
yeah. Yeah. Unfortunately, the PowerPoint doesn't show the figure anymore. I have this bug sometimes.
Yeah, so I mean, just
so you have the same ground truth all the time, yeah. So you have this ground truth optical flow field, and you produce your first flow estimate, and you have a loss there. Actually, all these parts of the stack are trained step by step. We also tried to train them all together, but that actually didn't work better, it overfitted. So it's better to train them all separately. So you have a loss at the end of the first network of the stack. If that was your question. And then you just give the warped image and the previous flow and the input images again as input to the next network, and it has to produce again the ground truth optical flow field. Yeah, so it has additional information at the input. So that's why the task is easier, and it can focus on the new task of refinement. But the ground truth data is the same. Was that your question?
Yeah. Well, I'm still wondering what is the function of the first 2 branches. I mean, how would you interpret the first 2 branches? I mean, instead of just 1 channel. So I mean, for the first version of the FlowNet, I mean,
yeah.
So you showed 2 architecture. Yeah, this
These
one.
2, okay.
Yeah, so I mean, how would you interpret that the first architecture? That
they're not integrated. So these are just 2 different approaches. So one is a FlowNet that just gets the 2 input images as stacked here as input,
yeah,
and produces the flow. And the other one is a different approach,
yeah,
and it has this special architecture here. And initially they had the same performance, but now we actually know that this one can work better.
Yeah, so I'm wondering why the first one can work better. How would you
because it makes this correlation more explicit. So it's actually not even clear how this network should solve this task, because you have some structures here in the first image of the stack, and you have the same structure somewhere else in the stack, and the network has to find out some features that matches these structures. And that's actually not such a simple task for a network. We analyzed that a little bit, so the network really focuses on certain areas, and then they grow together in this hierarchy, but we still don't know exactly on how this is done. Yeah, so this is some magic feature representation that is learned here, which does some kind of a correlation. But in this network, actually, this correlation is done explicitly. And that makes the whole learning procedure much easier for the network because it can focus on analyzing the cost volume and producing features that are useful for the correlation, and it doesn't need to learn the correlation as such. And that's why we believe this one works better than that one. But the difference is actually not that large.
Okay, thank you.
Yeah? I think there's a question over there.
Yes, question in the back. In processing a video stream, why are you not feeding the results from the last 2 frames to processing the next 2 frames? Obviously, the motion flow will be similar.
Can you repeat again? It's
Yes. Am I
a
loud
bit
enough
louder,
now?
maybe.
In processing a video stream,
Yeah.
why are you not feeding the results of the last 2 frames for calculating the result for the next 2 frames, when obviously the motions are more or less continuous, so the maps will be similar?
So you would use multiple frames and not just 2.
I would use the flow estimate from the previous 2 frames as a starting point, so to say, for the estimate of the next 2 frames.
But that's not really reasonable because the definition of your flow field is that you want to know the displacement vectors for the present frame to the next one, or the first to the second. And that's exactly what the network produces. So if you use the previous frame, so you mean if you have 3 frames, I'm not sure if
No,
I
I
understand.
would have the current frame.
Yeah.
Its flow estimate from the previous frame and the next frame.
So you have the flow estimate of the previous frame already.
Yes.
Okay. Yeah, that would be kind of a multi-frame approach. We have been working on that, and so far couldn't get any benefits from that. I agree that this should actually improve results because you have some temporal smoothness that you could exploit, and especially in the areas of occlusion, this should help. But so far we were not able to show a benefit.
Okay, thanks.
So that's more difficult than we thought. But I agree, this should actually improve.
So you mentioned that it's in general difficult to obtain the ground truth of flows. In medical imaging, sometimes it's necessary to estimate the motion of tissues. I'm just wondering if it's easy to transfer the model you learn from your flying chair dataset, for example, to the medical imaging tasks. If not, what will be the alternative solution you can suggest?
Can you repeat again? I didn't get the last part.
Yes, so in medical imaging, sometimes it's also necessary to estimate the motion of organs or tissues. Mm-hmm. I'm wondering also if you mentioned in general it's difficult to obtain the ground truth of flow.
Right.
So I'm wondering if it's easy to transfer the model you train on your flying chair data set, for example, to the medical imaging task.
Yeah, that's actually part 3, so that's maybe we should just go on. That's a very good point. So that's this cross dataset generalization that will follow now. Yeah, first of all, I want to highlight that since we are now doing learning instead of engineering, the emphasis of our engineering shifts to the data. So before, in a classical engineering approach, you got here your input, your output, and in between there were either some engineered modules or engineered features, and you had control about what you were doing there. And all the effort actually had to go in here. Now with deep learning, you have here the network parameters that are optimized on data. So actually you don't do anything in this part anymore. So this is all done by the optimizer, by a stochastic gradient descent, and becomes kind of a black box. You don't control it in a way. I mean, you control a little bit the architecture, but actually all the architectures are more or less the same. There are only details that you can optimize here. What actually makes a difference is the training data, which actually defines of what the optimizer will find as the system that will solve the job. Yeah, so that's why you have to focus much more on training data and data collection, data engineering than before. So the ideal deep learning scenario would be that your training and your test data are sampled from the same distribution. So that means that both data sets show the same type of variation, and there is no additional variation in the test set. Yeah, so really, training and test set, they are different, but they show the same kind of variation. And also, the second assumption is that the sampling density is sufficiently dense. Yeah, so you have big data so that you can really sample the variation that you see in the data, and you can learn from that. This scenario is true for most benchmarks. So for most benchmarks, you have a training and a test set, and they are sampled from the same distribution, so they are sufficiently similar. So that means if you train on the training set, then you're typically, if you do a good job, then you also are good on the test set. The common application scenario, however, often is very different, and you actually mentioned one of them. Yeah, your training and test data are sampled from different distributions. Yeah, so the training data could be the flying chairs data set, which is some synthetic data, and actually you're interested in the movement of organs and tissue, which is a different data set, but that's actually your application scenario. You want to solve that task. Yeah, so the problem is that now the test set shows new kinds of variation, and you need some kind of a domain transfer or gross data set generalization to use the training set to also solve the data in the test set. A second problem in practice is often that the training sets are small. Yeah, so especially on medical data, you cannot get thousands or millions of data samples, but you can only capture a little bit of the variation of the training distribution, and you cannot cover all the variation. Yeah, and that will typically lead to overfitting, and you have to be very careful about that. Most of you will probably know this already. So I want to mention here this overfitting problem. Yeah, so keep in mind that these deep networks have millions of parameters, and that's why they are obviously prone to overfitting. So just imagine, even if you have the ImageNet dataset with 1 million samples, and you have 60 million parameters, there are actually endless amounts of solutions to just overfit the data. Yeah, so actually from a machine learning perspective, it's very surprising that you don't overfit on this data. So the point is that there have been works on that the stochastic gradient descent, you have some implicit regularization, then you typically use dropout, you use other regularizers, and that's why you don't overfit. But always keep in mind, you have so many parameters that overfitting is always an issue in deep learning. And how do you see overfitting? Well, you see it if you compare your training curve, so the performance on the training data with the performance on test or validation data. And if you see something like that, that your training curve goes down and your validation curve goes up, then you have overfitting, and you shouldn't have this case. Yeah, so it's of course okay that your validation curve is above the training curve. That's how it should be, but it should drop. And if it goes up, then you have overfitting, and you either need more data or you need to regularize more. Yeah, so that's why this is here quite important in deep learning. First, check the training and validation curves, evaluate your network on a different data set, so to test actually this cross data set generalization, and visualize your results. So that's also useful, that you really look at what the network is producing qualitatively to see if it really makes sense what the network does, or if just the numbers look good, but you don't know actually how the numbers are created. So one way to avoid this overfitting is to use data augmentation. That's a long-known fact, and actually in biomedical imaging with this tissue, it's very convenient to use deformations as data augmentation. Yeah, so you're actually synthesizing a variation that is quite common in your data, and you know that, so you don't need to measure this variation by collecting samples. You can just synthesize this variation. So it's a very nice way to make better use of the little amount of data that you have. Yeah, and this is an example here. So you deform your image in a random way that still makes sense in a real image, and you also correspondingly deform the manual labels, and then you just have a new data sample that shows this variation that you want to learn. Yeah, and this is very powerful for many biomedical tasks. Other data augmentation transformations are color or brightness, things like that. Maybe I skipped this data generation process for flying chairs because I actually already mentioned it. What we also did is to use some synthetic 3D data set. Yeah, so we really rendered 3D scenes So this is one driving, where you actually have some objects, you have some scenes, and you can render the data and you can render the ground truth together with the data, and then you know the ground truth. And this is a way to produce variation in your target domain, possibly, or at least similar to your target domain, without the need of annotation. Yeah, the annotation comes here for free. Of course, the problem is that often the synthetic data sets are not really exactly in the domain that you're interested in. So you have some domain shift between the synthesized data and the real data you're actually interested in. And there are many approaches. So one is to really learn a domain transfer. And so this is, by the way, that's the last, that's this Flying Things 3D data set, very similar to Flying Chairs, but in 3D. Yeah, so this domain transfer would directly learn on how to transfer the features to the new domain so that you're good on this other domain. I won't talk about this here, but there are many works on that. So here a quiz about the different data sets that you have seen. So we have seen this Flying Chairs, which was a 2D data set. There was this driving data set that you saw at the beginning of the video. Moncar was this monkey that was animated, and then there was Flying Things 3D. And which one do you think yields the best optical flow results on the Scintille benchmark? Who is for A? B? C? D? Okay. So most of you are for D, and many have no opinion. So the correct answer is actually the Flying Chairs dataset performed best. And this was also a bit surprising to us because it didn't have this fancy 3D things and so on. The reason is that actually for optical flow estimation, simple objects are already sufficient to learn the optical flow, because what you want to learn actually is this simple concept of correspondence and how things occlude each other, and that they can rotate, that they can transform in a certain way. And for that, you actually don't need great objects in 3D space. You actually just need a few boxes or ellipses or polygons. So we did here an analysis, I probably won't go here into detail, analysis of different things that we moved in the images. You don't even need chairs, you can also just use some polygons like these with some holes in them and so on, and you already get the same performance as with Flying Chairs. Yeah, so a fancy data set for optical flow is actually not needed. You just need to show the variation that you expect in your final test set, and you need to show the variation that describes the problem of optical flow estimation, namely that objects move and occlude each other. The Flying Things 3D dataset that most of you preferred actually in the end really led to some benefits, because what we found is that the best thing is to first use Flying Chairs for training and then continue with Flying Things 3D. So you basically use this as kind of a fine-tuning. You have some kind of a learning schedule where you start with the simple data set first, and then you use a more complex data set to improve on that, to show additional variation that was not visible in the simple data set. Yeah, and we quantified that here. Yeah, so if you train just on Flying Chairs, you get this number. If you just train on Flying Things 3D, then you get that number, which is worse. And if you first train on Flying Chairs and then on Flying Things, then you see you get much better. Yeah, so this combination in the right order helps you. If you just mix them, you're not as good. Okay, I should finish it. Don't I have 15 minutes left? No? Okay, good. Then let's finish it here. It's anyway almost finished. There's a little bit of UNet here, but the take-home message, make sure that your training data covers all variation of your application scenario. Check for overfitting and prevent it by collecting or synthesizing enough data. And be careful with benchmark results if the benchmark is actually not representative for the application scenario you're interested in. Okay, thank you.